Hello, in today's video we're going to be talking about kinetic energy, which will strike a chord with any of you who are physicists or engineers, and we're also going to be talking about Graham's law. Now, if you are an engineer, you've probably heard about Graham's law before, but those of you who are chemistry or biology majors, most likely you haven't heard about this law previously. So we're going to move into the realm of physics starting today, and then we're going to continue on with this trend of more physics-based science for the next two chapters. So let's first talk about kinetic energy. I'm just going to show you some equations and what are involved in the equations, and then we'll discuss how those are derived tomorrow in class. So I don't want to focus a lot of time on the derivations. I kind of want to give you the punchline before we go through all the work on how we got to those punchlines. So the first thing is this kinetic energy. Let's say we're throwing a baseball or a tennis ball. We as scientists have equations that can identify the energy associated with this. The kinetic energy, which is the energy of motion of this big particle of a baseball or a softball or a tennis ball. So physicists have developed this a long time ago. Newtonian physics is based on this type of calculations. The equation for kinetic energy is the kinetic energy sometimes is written as this way. This is what physicists usually write, how they usually write kinetic energy. Our textbook writes it as this, the energy that's kinetic. It's just a different connotation. You'll see it both ways, but this is kinetic energy. Kinetic energy is equal to 1/2, I'll show you where this equation comes from tomorrow, times the mass of the object times the velocity of the object squared. Kinetic energy is equal to 1/2 mv squared. Now this is normally how kinetic energy is written. If we know the mass of an object and we know its velocity, we can determine the kinetic energy. If we know the kinetic energy and we know the mass, we can figure out what the velocity is of these things. Now the really cool thing about Newtonian physics is it's generally used for these big systems, motions of planetary bodies, softballs, baseballs, ballistics, things that you can see in everyday life. The kinetic energy, this equation, can actually be used in small systems such as an atom or a molecule. So unlike what's written up here, we tend to, and your books tends to, write the equation as E sub k is equal to 1/2 m, and a lot of textbooks do this, u squared. That u is the same thing as velocity. There's a lot of v's running around in chemistry, and so a lot of chemists decide to use a u when they write that equation. I am a physical chemist. I tend to write my kinetic energy equation, Ke is equal to 1/2 mv squared. Either way is fine, but your textbook uses this notation. So that's all I want to say about the kinetic energy. We have three different variables, kinetic energy, the mass, and the velocity. If we know any two, we can calculate the third one. I'll show you a little bit more about this tomorrow in class. So let's go to a different, so in order to figure out Graham's law of effusion, we need to figure out what the kinetic energy is of these particles. Now, we're going to go through a derivation tomorrow. I don't want to focus on it tonight in this video. However, I do want to talk about Graham's law. Let's say we have a beaker, an apparatus that's set up like this, and let's say there's a cylinder inside of that beaker that has a hole. Okay, so there's a disc inside of the beaker that has a hole that's and the disc separates two sides of the beaker. And let's say we have two different kinds of particles here, the dark particles and the light particles. Not like light particles, but lighter weight particles. These things are moving, they're gases, they're moving all around. Okay. Now, the hole is big enough to allow both of these particles to move through and be found on the opposite side. So of course we're going to have both types on the left and the right because the particles are moving back and forth between this disk. So let's say we have that. Let's say we have this going on. Now Graham's law, this is called effusion. Effusion is the ability of a particle to move from higher concentrations to lower concentrations. It's kind of like osmosis. So this particle, the effusion, is able to move around on this side of the system, find the hole, and be found on that side of the system. We also have diffusion, which is very similar to this, and I'll talk about that tomorrow, but for right now, this is just effusion. So, based on mass alone, we should be able to identify if we had everything starting on the left and we let time run such that we have these particles moving around, we would find certain amounts of both types on the right. Now, how in the world do we know how many of each type are found on the right? That's a little bit more tricky to find out the exact number. What we can do is we can find the relative ratio of dark spheres to light spheres. Okay? That's what Graham's law of effusion tells us. So, in order for us to do that, we should think about the mass. We know that lighter particles, lighter weight particles, lighter mass particles, they move quicker than heavier mass particles. This makes sense. Lighter things tend to move faster than heavier things. A small bird can fly much quicker and change directions very quickly compared to a big, like pelican. They don't move very quickly. Their mass is too large to move quickly. Same thing is happening here. So if we did a thought experiment on this, we would assume that whichever particle is lighter in mass, smaller in mass, more of them would be found on this side after a given amount of time than the heavy ones. The heavy ones are slower. They take a long time to travel around inside this left side of the apparatus. The lighter particles move very quickly. They can find the hole much more efficiently. That's what Graham's law tells us, and that's what we actually get. The rate of A, we'll call one of these A and one of them B, divided by the rate of B, so these are the ratio of the rates, is equal, and I'll do the derivation tomorrow in class, is equal to the square root of the molar mass of B divided by the molar mass of A. This is taking Graham's law of effusion, working with chemistry terms. We're using molar masses. You'll notice that rate A is on the numerator on the left, rate B is on the denominator of the right. The molar masses are flipped. So let's do an example. Let's say we're taking, I think this is helium, and then the other one I want to say is methane, CH4. So we know helium's molar mass is found on the periodic table as 4.003 grams per mole. We know that methane's we can also calculate from the periodic table. That's given as 16.04 grams per mole. Great. Let's say that these colored in spheres over here are helium. And let's say that the ones that are not colored in are methane. Okay. Let's see the relative rates of these things. We're going to plug in we're going to put this into the equation. The molar mass of B, which is the 16.04 grams per mole, divided by the 4.003 grams per mole. We plug this into a calculator. We end up getting 2.002. The grams per mole, those units kind of cancel out. This is the square root. This tells us, this 2.002, we can really write it out as 2.002 to 1, tells us the relative ratio of these particles going from the left-hand side of the apparatus to the right-hand side of the apparatus. The rate of A, and in this case A is helium, is twice as much as the rate of B. What that means is we should find twice as many particles of helium on the right as we do particles of methane. Helium is traveling around twice as fast compared to the methane, which means that it can find the hole twice as quickly. And this is how we can use Graham's law. It just uses the ratios of molar masses to identify the ratio of the rates. With that, I want to stop with kinetic energy and Graham's law. I want to go on to a new topic in the next video. So we'll be talking about this tomorrow in class. I'll be going through some derivations. And with that, I want to say have a great night.